So here's a problem where if you release an object of mass m at zero velocity at a distance of 2 times 10 to the 6 kilometers from the core of the Earth, what is the velocity at which the object hits the Earth? And we're going to ignore the other planets in the solar system here. So you're given that you're releasing this object at no speed really. You're given distance away it is from the core of our planet Earth, and they want you to figure out here how fast is it going to go right as it impacts. So you want to think of it as, okay, you got your planet Earth, and our object is, just released from planet Earth, and it's going to travel this distance, and it's going to impact at some point. So this distance they give us here is this distance right here. Well, really, it's the distance from the object to the very core of Earth. And we got to worry about, this point, which we'll just call point A, and we got to worry about this point, which we'll just call point B. So it's going from point A to point B. It starts at point A with nothing. It's just floating there. It's pulled by Earth's gravitational field to point B, and by the time it gets to point B, it does have some type of velocity to it, and we're going to try to figure out what that is. A couple values you can just, you'll either be given or assume you can look up or known. Things like the radius of the Earth. The radius of Earth is estimated at 6,378 kilometers. And we're going to need that in meters, so I'll just do that now at, we'll just put in scientific notation, 6.38 times 10 to the 6th meters. The mass of Earth is something that we're also going to need, you'll see. And the mass of Earth is estimated at 6 times 10 to the 24th kilograms. It's huge. And there's a couple other values that you can assume are constants or either given or known, and I'll get to that in a moment. The main thing we're going to be using here is the idea that your initial kinetic energy and your initial potential energy are equal to your ending kinetic energy and your ending potential energy. So our initial kinetic energy, which I'll just call kinetic energy at point A, plus your initial potential energy, which I'll call potential energy at point B, is equal to your ending potential energy or your ending kinetic energy. So K, your kinetic at point B, and your kinetic or your potential at point B. And excuse me, I meant to put A here. So each of these values can be calculated. All right, kinetic energy is just calculated by 1/2 of mass times velocity squared. And this is our velocity at point A, and this is our mass at point A. Okay, simple enough. Our potential energy is calculated based on the gravity of Earth, and this is a value that's you can look up how to calculate potential energy of a planet very easily. It's in all physics textbooks. It's based on it being a negative value. It's based on being this little m times big M times g over r. The little m is your object. In this case, it's our object here at point A that's released. The big M is your larger object. In this case, it's Earth. So I'll put the m of Earth. And here is g, a gravitational constant number. It's always the same, divided by your radius. And this is a negative value here. So that's going to be our potential at point A. And then we got our kinetic energy at point B. Again, we're going to do the same thing, 1/2 of mass times velocity squared. Again, this is at point B. And then potential, same thing. It's just negative little m, our mass of our object, times the mass of your larger object, in this case Earth, times that gravitational constant divided by the radius. The radiuses are different between the two. At point A, we got a radius A, which we're given the value of over here, and then we got at point B, we're going to have a different radius. We'll just say radius of B. So those are two different values. So the radius of B is going to be actually just easily enough, it's just going to be the radius of Earth. All right, so first thing we notice here, the kinetic energy at point A. It's released with zero velocity. So our V of A is 0. So this whole value here is 0. Ka is insignificant in this problem. It's of no use to us. Potential energy at point A is very important. We're going to calculate that out. Kinetic energy, it's also very important because we need to calculate the velocity. And then potential energy at point B is very important also. So what you can do now is you can just forget about Ka, and we can plug in all these other values here. So if we do that, if we just plug in everything and just write it all out, we got A minus mass of Earth. This is the mass of our object, remember. G is just a given gravitational constant, which I'll write out in a second. This is equal to plug in KB. This is at point B. And then plug in U of B. Since it's negative, I'll just put minus over radius at point B. All right. First thing you should notice, M, M, M. You can cancel all those out. The mass of the object doesn't matter. That's very important here. The mass of the object does not matter on its velocity when it gets to point B. That's very, very helpful here. Everything else we know, or is a constant. Gravitational constant is a constant value. The gravitational constant, and again, this is, you can look this up very easily, 6.67 times 10 to the negative 11th power. What this number represents is basically, it shows you how small the force of gravity actually is. If you were to take two objects that were both like 1 kilogram and have them 1 meter away from each other, this would be the force of gravity in newtons on the objects. So gravity is a very small force just when you're talking about small objects, but when you come to planets, it's a very important force because planets are so large. So we can plug this value in at G, all right. Mass of Earth, that's a known value. We got that here in kilograms, so that the units there are good. And the radius of point A and point B are two different values. So the radius of point A is, again, that's what we were given here, 2 times 10 to the 6 kilometers. That's in kilometers. We need that in meters. So it's actually going to be 2, we're going to use 2 times 10 to the 9th for meters. And we'll plug that in for A. And then at B, it's closer to Earth. It's just the radius of Earth, which I wrote out earlier here. So we'll use 6.38 times 10 to the 6 meters. If you rearrange this, you know, just basic math principles, you would actually get to M of E. Let me move down here. M of E times our constant here over R of B minus M of E times our constant, R of A. This is equal to your 1/2 velocity squared at point B. And again, that's what we're looking for here. You could rearrange this into velocity is equal to the mass of Earth times gravity minus 1 over RB, or excuse me, times 1 over RB minus 1 over RA. And you could square all that. This is basically just breaking it down. I'm going to stick with this first version over here on the left, but you can easily see how you get that. So if you just plug in all your values here, it's basic math at this point. It's just 6 times 10 to the 24th power. That's our mass of Earth. The constant, 6.67 times 10 to the negative 11th power over RB, again our RB value. And you subtract that from 6 times 10 to the 24th kilograms, again the mass of Earth, times the gravitational constant. And this, again, this is RA now. This is the initial value we were given. And that will give us, that's equal to still 1/2 velocity squared. So again, you know, just basic math at this point. This comes out to, this whole value comes out to 6.27 times 10 to the 7th. And you subtract that from, this whole value comes out to 0.02001 times 10 to the 7th. You know, you just 2 times the square root of 6.25 times 10 to the 7th. And that will give you your velocity, excuse me, which is equal to 11,180, or 1.1 times 10 to the 4th meters per second. And that's it.